already. And then we'll also look at sort of where we're going, because this whole chapter of kinetics, right, it's chapter 14, it's chemical kinetics, is all about rates of reaction. And really the overarching theme here is what affects the rate of reaction? You know, how does concentration affect it? How does time affect it? How does temperature affect it? What are the different handles that we can pull to modify the rate in one way or another? So the first thing that we talked about was how concentration affects rate. Right, so we talked about collision theory a little bit. If you increase the concentration, generally the rate of the reaction increases. So that was we had the overall rate expression. And that was for like a generic reaction of A plus B gives you C plus D. And I'm not going to write out the whole rate expression, but if we wanted to get this overall rate from one of the reactants, we'll say A, then that was going to be, or then that would be negative 1 over A times the change in the concentration of A over some change in time. That was fine. That gives us a way to calculate the overall rate. It also lets us sort of have average rates for a reaction with regard to a single reactant, and we can calculate for those other reactants as well. But if we want to look at just the specific rate of one reactant, that's where we got into the rate law. So let's look at a simpler reaction now, just A turning into some product P. So the rate of this reaction, if it was first order, would equal K times the concentration of A raised to the first power, right? So if we increase that concentration, it's a first order reaction, then our rate goes up. And then there's some proportionality constant there, which is K. And K equals the rate of, well, K is based on the rate of reaction when the concentration of A is 1 molar, right? Because if the concentration of A is 1, then K equals the rate. And then we also had like a second order reaction where the rate would be equal to K times A to the second, or 0 order, where rate equals K, I'm going to write it in here, times A to the 0. So first, second, and 0. So for different reactions, under different conditions, right, the rate is dependent on concentration, and then that can change depending on those concentrations. And that's kind of everything that we've covered so far, really, right? We've really just looked at concentration and how that affects the rate. And the next thing that we're going to do is we're going to look at how time affects the rate. So how does time affect concentration? I think I'm using the right effect, time effects. Because we know when we looked at these early equations for that average rate or the instantaneous rate, we couldn't use that to predict anything about the future. It was just for that one moment in time. Right, so that leads us now into where we're going, and then, or what we're going to talk about today, so this will be today, and then, yeah, Thursday, we'll talk about how temperature affects, well, how temperature affects rate, really. Although we know that rate and concentration are tied, right, linked together. All right. So the key to this is the integrated rate law. So it involves some calculus. We're not going to get into the calculus. If you want to look up more, in the book it explains how to derive the integrated rate laws. I'm just going to show them to you, and we're going to manipulate them a little bit. But the integrated rate law gives us the relationship then between concentration, between concentration of a reactant and time. Right? So that gives us the relationship. And then as we change, or as the reaction proceeds, we can now predict out to the future with the integrated rate law what the concentration will be at a future time. We could even go backwards and say what the concentration would have been earlier in the reaction. And we're going to look at 3 different integrated rate laws because depending on the order of the reaction, the integral changes. And so the result is different. The first one that we're going to talk about is the first order integrated rate law. And this one in a lot of ways is the most useful because most things follow first order kinetics. I think I mentioned at one point that some of my research involved fumigating, post-harvest fumigations, and the rate that that fumigant gets absorbed into the commodity that you're treating, could be fruit, could be cars, could be seats, could be all kinds of different things. Well, not even really roughly, pretty much follows first order kinetics. And so you can use that to model it. And if we think about collision theory again, that also makes sense because the rate that it absorbs is dependent on that molecule colliding with the surface and then the chance that it sticks to that surface or goes into that surface rather than just bouncing off again, which is the same way that first order kinetics works, where you have to have a collision to have a reaction. So to get the integrated rate law, sorry, I got ahead of myself a little bit. We've been looking at our rate law, or differential rate law, as the rate equals K times concentration of A. We also know that the change in concentration of A over some change in time is another definition that we have of rate. So we can set these 2 expressions equal to each other to get the differential rate law. And then this is what we integrate to get the integrated rate law, integrating with respect to T. So after you do the integration, again, you can look that up in the book. We'll get the natural log of A at time T. So this is the concentration in the future is equal to negative, this is key too, that is negative times the rate constant. The rate constant is going to be positive, but you plug a positive number in, multiply it by negative, and it becomes negative. T is like the amount of time, right? So for whatever point in the reaction that we want to know, and then our natural log of A sub 0, meaning our initial concentration. So if we plug in an initial concentration, plug in K, we can say for any time in this reaction, what is the concentration going to be? So actually, let me point this out too. Notice that this is a straight line. That's going to be a theme in a lot of these. And also, actually, I think I'll point this out on the next couple slides. So if we take some reaction, some process, this is sulfuryl chloride decomposing into sulfur dioxide and chlorine gas. So this concentration of sulfuryl chloride was monitored at a fixed temperature as a function of time during this decomposition reaction. And then they created this table of data. We've got the SO2, or the sulfuryl chloride concentration, right, from 0 seconds all the way up to 1,500 seconds. So what we can do to show that this is first order by graphing is we take the natural log of all of the concentrations, and then we plot those versus time. And you'll get, if it's first order, you'll get a perfectly straight line. And then the other cool thing about the integrated first order rate law, and actually all the integrated rate laws, is that they have, so this will be for sulfuryl chloride, SO2, Cl2, right, at time t equals negative K times T plus the natural log SO2, Cl2, 0, which is the initial. The integrated rate laws all have the same format as a linear, or as the equation of a line. So y equals, in this case, negative, mx plus b. Right? So when we integrate these rate laws and rearrange them, you're doing so to get this relationship. Because when you graph it, what is the slope? K. Right? So the slope of the line is K. So we don't even have to solve for K. If you have Excel or something, you can graph it, and it'll give you K for that equation. So then our rate constant is just going to be the slope. And now, because the negative is part of the integrated rate law, the K is a positive value. So K will be 0.000290 or 2.9. I'm not sure why it's only 2 sig figs in the answer up here, but 2.9 times 10 to the negative 4, and then inverse seconds. The other cool thing is that this equation also gives us our initial concentration. So even if you start a reaction and you forget to do your initial concentration, you can measure the rate of, in this case, decomposition, measure the concentration over time, and then you can back calculate to your initial concentration. Or just plot the slope or plot the line, and the equation will give it to you. Specifically, it'll give you the natural log of SO2. So here it would be negative 2.30. So what if we wanted to predict out to some time in the future? Let's say at 1900 seconds, what would the concentration of sulfuryl chloride be? Well, we can just write in the equation. SO2 CO2 equals negative KT plus natural log. And then we can just plug in the numbers from the line equation of the linear regression. So this will be negative 2.90 times 10 to the negative 4 times our time, 1900 seconds, plus a negative 2.3, so minus 2.3. So negative 2.9 e to the negative 4 times 1900 minus 2.3. So how do we, well, you'll get this. And then this will be negative 2.851. So how do you sort of undo a natural log? E, right? Yeah. Raise it to the power of E, which is the natural base. So the concentration of SO2 Cl2 will be equal to e raised to the 2.851. Or 0.0578 molar. So as long as you can remember the equation for the integrated rate laws, they're not that hard to use. Just kind of plug in some numbers, get some answers. Some of the Alex questions get a little bit tricky, and I was going to go over some. We'll see how much progress we make. My laptop is one of the devices that's been plagued by the unable to connect to the internet on the Wi-Fi. My phone and my iPad, fine. Laptop won't do it though. Okay, so if we have cyclopropane rearranging to form propene in the gas phase, the reaction is first order in cyclopropane, has a measured rate of 3.36 times 10 to the negative 5 inverse seconds at 720 degrees, well, not degrees, 720 Kelvin. If the initial cyclopropane concentration is 0.0445 molar, what will the cyclopropane concentration be after 235 minutes? So how would I set this one up? It's first order. We have time. What's the equation for the integrated first order integrated rate law? Yeah, natural log concentration of cyclopropane, which is C3H6, time t. It's going to be equal to negative. Yep. Yeah, we can just plug the numbers in here. So this will be 3.36 times 10 to the negative 5 inverse seconds times our time. Yeah, so our time here is in minutes, but K is in inverse seconds. So two things you could do. You can either convert K into minutes, or you convert your time into seconds. I think that's right. Yeah. So that many seconds plus the natural log of our initial concentration. So that'll be 0.0445 molar. All right, and now solve for concentration of cyclopropane at 14,100 seconds. This. Any questions so far? Make sure you don't forget the negative on the 3.36 times 10 to the negative 5. Okay. Is everybody good on this one? Yeah? All right. Is everybody just super tired? I can see it. See it on everybody's faces. That's why I went and got a Mountain Dew, which I'll pay for later, and not being able to go to bed. All right, so that was the first order integrated rate law. For the second order integrated rate law, it's the same setup, except now our rate law, well, this portion of our differential rate law is K times concentration of A to the second. This portion stays the same. Now our differential rate law is going to be this, right? So it's still the change in concentration of A over time, but now it's equal to K times concentration of A to the second. And that has ramifications for the integral, again, which I'm not going to do the whole integral. We'll just jump to the integrated rate law. This is the form, the second order integrated rate law, which, by the way, I will give you these rate laws on the exam. You don't need to memorize the form because, like I said, I did a bunch of stuff with kinetics in my research, and I had to look up first order integrated rate law every single time. It's a very, very easy thing to find. Now we'll probably have it memorized. Okay, so for the second order integrated rate law, we also get the same form for an equation of a straight line. But instead of being the natural log of each of the concentrations, it's the inverse of each of the concentrations. So we have 1 over the concentration of A at time t is equal to Kt plus 1 over the concentration of A initial. And then instead of K here being multiplied by a -1, we have a positive slope. So yeah, if you plot this 1 over the concentration of A versus time, you get a straight line. All right, like I said, with the integrated rate law, or with the first order integrated rate law, it's the natural log versus time. Second order is 1 over the concentration versus time. And we'll get to zero order too. So similarly, we can use graphical analysis to determine if our chemical reaction is first order or second order, right? Just by graphing it, without doing the whole. Let me think about this. Because the other way that we did it before was to take the method of initial rates. So you would start a reaction at one concentration, then change that concentration, see how the rate changes initially. But now we can do it graphically with these integrated rate laws. I feel like there was something there that I wanted to say. But so if we take this reaction and we graph it, zoom in on this, and we graph it like it's a first order. So we'll say we don't know that if this is first or second order. So we say, okay, let's assume it's first order, graph the natural log of the concentration versus time, like we would do. And then if it was first order, this would give us a perfectly straight line. We can see that it's got some curve to it. And because it has that curve, we know it's not a first order. It's not a first order reaction. So then we can go through and we can graph it again as 1 over the concentration versus time. And if that gives us a perfectly straight line, then we know that it's a second order reaction. And again, we can use that equation, the equation of the line, when we plot 1 over the concentration versus time, to get the K value, as well as to get the initial concentration. So again, this is the form, NO2 here. Nitrogen dioxide. So 1 over the concentration time T is equal to Kt plus 1 over the initial concentration Okay, so we're going to solve for 1 over NO2. So K is, yeah, 0.255. T is going to be 2,000 seconds. Actually, I should write this in too. What are the units for K for a second order reaction? Yeah, M-1, S-1. It's always going to be 1 minus the order of the reaction for M. So first order reaction, it's 1 minus first order reaction, so 1 minus 1 is 0. So it's just S to the minus 1. For second order, it's M to the minus 1. Plus our initial concentration, well, our 1 over our initial concentration. So it's going to be, it's actually just going to be 100. Because that 100 is already 1 over the concentration to make it the straight line. Right, yeah, so just 0.255 times 2,000 plus 100. So 1 over the concentration, NO2. This is going to be 610. Actually, this is going to be 610. This is actually going to be inverse molar. This happened when I did this before too. There's something I'm missing. Oh, right. We're adding them. So this is still inverse molar. I'm always thinking multiplication, but right. So we multiplied 2,000 seconds times 1 over seconds. Then we get 1 over molar. This concentration is already 1 over molar. So we can add those together. The units stay the same. And then to get our answer here, we just do 1 over both sides. Right? Take the inverse of both sides, which could look like this. Raise each side to the -1. So it's going to be 0.00164 molar. Cool. Easy. Plug numbers in. Alrighty. So it's same thing for the second order. You just have a different equation. Yeah. Now the zero order integrated rate law is now K raised to, or K times A raised to the 0. So it's just K. So the change in concentration of A is just equal to K. But when we integrate that with respect to time, the concentration is going to be different at time 0 versus time t. And we get the easiest equation, which is just concentration of A at a time is equal to -K times t plus the initial concentration. And again, we're given an equation for a straight line, where the slope is -K. Alrighty. So the half-life of a reaction is the time. Oh, wait. OK, well, I want to summarize here real quick before we move on to half-life. Right, so there are 3 ways now that you can check the order. Well, 2 ways you can check the order of an equation now. Right, you could do method of initial rates and determine if it's first, second, or 0, first, or second order. Or you can graph it. And the graphing is going to depend well, three different types of graphs. One is going to be just the concentration of A versus time, 1 over the concentration of A versus time, or the natural log of the concentration of A versus time. And if it's 0, first or second order, it'll be linear on one of those graphs. Okay. So for half-life then, the half-life is the amount of time it takes to get to half of your initial concentration, or to just half of your concentration, really. So if you had an initial concentration of 0.5 molar and the half-life is 50 seconds, what would the concentration be after 50 seconds? Starting at 0.5 molar. Right, so after 50 seconds, it would be 0.25. What about after another 50 seconds? Yeah, it would be 0.125. Yeah, so every time you're cutting in half the concentration that you ended out after the previous one. Put this another 50 seconds. I think that's probably the hardest thing about half-lives, is just remembering that. It's not how much, it's not always half of what you started with. 2 half-lives doesn't equal 0. 2 half-lives equals 1/4. But half-life expression is different for different reaction orders. So if we have a different reaction order, half-life is going to, the calculation for half-life is going to be something else. And you can derive those half-life equations pretty easily from the integrated rate law equations, right? Because again, integrated rate law equations are telling us the relationship between concentration and time, how it changes over time. So it'll tell us something about half-life. So the trick for deriving these, now this is just the, let me write this out. This is the first order integrated rate law, but rearranged because it's easier to work with for this if you rearrange it. All right, so that's the first order rate law. If we take this and we subtract natural log of A0 from both sides, then a property of, I guess I should just show this. One of the properties of natural logs, or logs in general, is if you have a natural log minus a natural log, that's the same thing as the natural log of the first thing divided by the second thing. So at half-life, or after 1 half-life, so when t equals t1/2, the concentration of A at 1 half-life is just going to be half of your initial concentration. So we can take this equation, and we just plug in 1/2 A0 for AT. So we'll get the natural log of 1/2 concentration of A0, right? So half of the initial concentration divided by the initial concentration equals negative KT. So for a first order reaction, because we're taking A0 divided by A0, the half-life doesn't depend on the concentration. The initial concentration doesn't change your half-life. So yet, because there's no room here, this is now the natural log of 1/2 equals negative K times T. This is, sorry, specifically T1/2. So if you want to calculate the half-life for a first order reaction, oh, right. It's just the natural log of 1/2 divided by the rate constant. Or the other way that you'll see it written out would be 0.693 over k equals t 1/2. Because 0.693 is the natural log of, well, it's the negative natural log of 1/2. And this is unique to first order reactions. So if you get a problem on ALEX, which you probably will, because I did them, where it tells you what the half-life is for some reaction, and then it asks you to calculate this stuff. You're like, well, which equation do I use? How do I know if it's zero, first, or second order? Well, if the half-life remains constant, then it's a first-order reaction. And so you would use that half-life. This equation, or the first order integrated rate law. Okay. So here's that expression again. This is the more common one. It's just the half-life of a first order reaction is 0.693 divided by k, which again is unique to first order reactions. I'm going to do this a little more later, but part of the reason this is in a first order reaction, the rate is directly proportional to the concentration. So if your concentration gets cut in half, your rate also gets cut in half. So the reaction slows down at the same rate that the concentration drops. So the time that it takes to get to another half always remains the same. All right. So we've got half-life here, or half-lives here, right? We're looking at a first-order reaction. Good to know, from A to B, A reacting to form B at various times during the reaction process. The black circles represent A, and the red circles represent B. What is the half-life of this reaction? Let me zoom this. Wow, you can't even see. Those are all black. Okay. These two are red. I'm going to circle the red ones. So at what time have we gone through one half-life? Yeah, why 90 seconds? Yeah, it's 50-50 at that point. There's 10 total dots. So we start out with all of them black. At 90, we've got 5 red, 5 black. Or here, 5 circled, 5 not circled, as far as you can tell. So 90 seconds, right? Half-lives. How about this one? Again, we've got a first-order reaction, A reacting to form B, has a half-life of 25 minutes. If the initial concentration of A is 0.300 molar, what is the concentration of B after 50 minutes? Don't use a calculator. What was it? What's the concentration of B? So if the first half-life, we got A here, B here. After one half-life, it's going to be 0.15 molar, 0.15 molar. How about after a second half-life? Definitely when I was going over this one before, I was like, the answer's not there. It should be 0.75. But it's asking about the reaction of B, how much B is produced. This is kind of like, you guys do ice tables in Chem 1? Some fearful looks. We'll get to those. We'll do them more. Yeah, so it's B in this case, 0.225. Because in each of these steps, well, that's our initial conditions, right? Half of it is being converted over every half-life. And it's happening at a consistent rate again, too. Right? So each time here we've dropped exactly 1/2. That's not going to be the case for 0 and second order. We have one more here. So first order reaction has a half-life of 26.4 seconds. How long does it take for the concentration of the reactant in the reaction to fall to 1/8 of its initial value? I think in some ways this is one of those problems. I'll let you think about it for a bit. Yeah. So one of the ways you could look at it is say, you can just throw some numbers in. Let's call it 1 molar. So after 1 half-life, it'll be 1/2. And then after a second half-life, it'll be 1/4. And a third half-life, it'll be 1/8. And so then each of these is going to be 26.4 seconds. But yeah, once you figured out how many half-lives, then you just take the, once you figure out how many half-lives, then you can multiply the half-life by 3, or by the number of half-lives that you need to go through. You could also, I think this is the easier way to do it, but just because I think it demonstrates a nice thing about this. We could also, instead of doing it this way, we could, maybe I don't want to do that. So we could calculate K. So, well, let me do it this way. 0.693 over K equals T1/2. So all we have to do is plug in our half-life. We get 0.693 equals 26.4 seconds. So 0.693 divided by 26.4 equals K. And notice that does give us that gives us also the correct units for K for a first order reaction. It's just 1/seconds. So once we've calculated K, we could use the first order integrated rate law. I'll just use the generic A0 or AT equals negative KT plus natural log of the initial concentration A0. So like for a half-life, we just plugged in A0 is equal to, concentration of A at 1 half-life is equal to 1/2 times the concentration of A0. But for this question, we want to know what 1/8 is. So instead of saying, at 1 half-life, how long, so it's just going to be T now, will it take us to get to not 1/2, but 1/8 of A0. And then we'd have the natural log of 1/8 well, it could make it even easier. Sorry, I probably made this more confusing. So I'm just going to put in 1/8 here, because the half-life of a first order reaction does not depend on the concentration. It doesn't matter what our concentration is, it's going to be constant. So we can plug in any concentration that we want. We could say that we're starting with a concentration of 1. How long does it take us to get to 1/8? So without actually calculating any numbers, this will be t plus, and conveniently, the natural log of 1 is 0. So this will be 0. So now it's the natural log of 1/8 divided by our k, and that will tell you, I guess I should do this. 1 divided by 8 divided by negative 0.693 divided by. So t equals 79.2 seconds. And 26.4 times 3 is also 79.2 seconds. So maybe a little more complicated. Could work when it's not a even number of half-lives to get there. Because what if instead of 1/8 of the concentration, it said 0.31415967877, right? Like some random long number that's not an even fraction or not an even multiple of 2. This is how you would do it. Okay. So what do you think we're going to do for this? For a second order rate law, integrated rate law, if we want to know the equation to calculate half-life, we're going to do the exact same thing. We're going to replace AT with half of A0. So 1 over, I'm just going to call this, instead of writing out the whole thing, just A0 equals KT plus 1 over A0. So when I subtract A0 out from both sides, we'll get, oh, actually, before I subtract that out, this, we can make this a little bit easier to look at. If it's 1 over 1/2, it can be 2 divided by. So it'll be 2 over A0 minus 1 over A0 equals KT. So then it'll be 1 over A0 equals T, and this is T1/2. So for the second order rate law, the half-life is dependent on your initial concentration. So as your concentration changes, your rate also changes. I'll show that a little bit better later, but you can still use this to calculate, right, half-life. Or if you have the initial concentration and you have the half-life, you can use it to calculate K. So there it is again. T1/2 is half-life equals 1 over K times the initial concentration. So a lower initial concentration gives a longer half-life. So as this reaction proceeds, it takes longer and longer and longer to cut your concentration in half. Because if you think about what's happening in a second order reaction, we have to have, two separate molecules, atoms or molecules, collide together. So as there are fewer and fewer of those, we're not decreasing at the same rate that our concentration decreases. It's decreasing at the rate squared of the concentration. So if our concentration drops in half, our rate decreases by 1/4. And then if it decreases by another half, then it decreases by 1 over 16. So it's slowing down faster than the concentration slowing down. Then for a zero order reaction, again, we do the same thing where we just replace AT with A0, 1/2 A0 equals negative KT plus A0. So if we have 1/2 A0 plus, or subtract A0 from both sides, right, we're going to get a negative 1/2 A0 equals negative K times T 1/2. So A0 over 2K equals the half-life. So how do you think that this is going to affect half-life? As our concentration's decreasing, is the half-life going to get larger or smaller? Smaller, right? As A0 goes down, it's going to be more directly proportional to the time, or the half-life. So for zero-order reactions, again, our half-life is dependent on the initial concentration. But unlike the second order, so for second-order reactions, as the initial concentration goes down, the half-life goes up. For zero-order, as the concentration goes down, the half-life goes down. So it takes less and less time to get to half of your initial concentration. So half-life's getting shorter as the reaction proceeds. So I was thinking about how do I try and make this more intuitive or help you guys see this. Oh, I guess I have it after this slide. This is a slide, this is a summary. But I just wanted to look at if we had some hypothetical reactions, right? So if we have a zero-order reaction, what's true about the rate in a zero-order reaction? How does concentration affect a zero-order reaction rate? It doesn't, right? So if we go through one half-life here, actually let's calculate, or we don't have to calculate it really. So if we have a concentration of 100 molar, which is insane, but if we have a concentration of 100 molar and we're decreasing at a rate of 1 molar per second, what's the half-life going to be? Well, I guess. Yeah. How long is it going to take us to get to one half-life? From 100 molar, if we're decreasing at a constant rate of 1 molar per second. 50 seconds? I think that works out. If K is 1. Right, so 50 seconds. But starting from an initial concentration of 50 molar, now our rate, because this is zero order, is still 1 molar per second. So we're still decreasing at that same rate. K is still the same. So if we wanted to calculate the rate, now our half-life is just going to be 25 seconds. Right? And if we decrease our concentration again, it's going to be decrease that half-life again. Because the rate's not changing, the concentration is. So it'll take less and less time to get to half because you have less stuff and it's disappearing at the same speed. For a first-order reaction, though, if we're starting out at 100 molar and we have 1 molar per second, what's our half-life? Wait. Oh, I knew I was missing some piece. This is still going to work, but this is actually, we do need to calculate this. So our half-life is going to be equal to our initial concentration, which is 100, over, oh yeah, it did work out right. 2 times our K, which is 1, yeah, molar per second. right? So the half-life here would be 50 seconds. Now if we want to calculate half-life with an initial concentration of 50 molar, it's 50, our rate's the same, K is the same. So it's still 2 times 1 molar per inverse second, so 25 seconds. Okay. So if we want to calculate the rate, what's the rate for, or sorry, what's the half-life going to be, these set of conditions for first order reaction? What's the equation?
0.693.
Yep, 0.693 over K. So 0.01 inverse seconds here. So it's going to be 69.3 seconds. So okay, let's move forward in time 1 half-life. So now we're down to 50 molar. Our K is 0.01 seconds. But we need to calculate the rate now, right? Because for a first order reaction, our rate depends on the concentration. So if you want to calculate the rate, that's going to be rate equals K times the concentration of A. So the first one I calculated it for you, but for this one it's going to be 0.01 times our concentration of A, which is 50. So now our rate is only 0.5 molar per second. So our half-life is going to be, oh wait, it's the same thing. Right, because the equation doesn't depend on the concentration or the, well, rate really at the time. It just depends on K. So our half-life is still going to be 69.3 seconds. And then we can go to another half-life, and that half-life is going to continue to remain the same. But our concentration, every time it cuts in half, our rate is also going to cut in half. Everybody tracking so far? So what do you think is going to happen for the second order reaction? Kind of already said it a few times. Let's see, the half-life equation is going to be 1 over K times A. So if we want to calculate the half-life, it's going to be 1 over K times our initial concentration. Is that it? There's nothing else? Yeah. So 1 divided by, let's see, K times A, 0.0001 times 100. Our half-life is going to be 100 seconds. So if we move forward in time, 1 half-life, to 50 molar, K is always going to be the same. So what is the rate going to be for 50 molar and a K of, what's the equation for the rate? K times concentration of A squared. So it's going to be 50 squared times 0.0001. So now our rate is 0.25 molar per second. Our half-life again is going to be 1 divided by 0.0001 times K, or sorry, no, K times the concentration is 50. So now our half-life is 200 seconds. So, and like I said earlier, right, if we cut our concentration in half, our rate is now 1/4 of what it was before. If we cut it in half again, it's going to be 1/8 or 1/16 of what it was. Actually, let's do that real quick. So if we go down to 25 molar for this one, again, K is constant. That's why it's called a constant. So now it's 25 squared times 0.0001. So rate is going to be 0.0625 molar per second. Yeah, which is 1/16. So this is why the half-life slows down for second order. Because as you deplete all of your reactants, the reaction is very, very dependent on those reactants being around. So you're going to have a huge impact on your rate. Are there any questions? Any concerns? Cool. So let's sum this up a bit. Or one last question then. A decomposition reaction with a rate that is observed to slow down as the reaction proceeds has a half-life that depends on the initial concentration of the reactant. Which statement is most likely true for this reaction? Why C? Well, yeah, but why does it quadruple though? What is it about this reaction? It's a second order reaction. Because the rate's slowing down as the reaction proceeds. So as the concentration of the reactants decreases, it slows down, means it's a second order. So yeah, then it's going to be C. Ignore that. Oh yeah, there's one. So what if the reaction slowed down as the reaction, well, yeah, the rate slowed down as the reaction proceeded, but the half-life did not depend on the initial concentration. So the reaction slows down as it proceeds, but the half-life does not depend on the initial concentration. Zero order, the reaction rate would remain constant, and the half-life depends on the concentration. So it would be a first order. So then a plot of the natural log of the concentration of the reactants as a function of time would be linear. So if it was a first order reaction, then A would be true. And then if the reaction didn't slow down as it proceeded, and the half-life did depend on the initial concentration, it would be a zero order. All right. We will get to the effect of temperature on rate on Thursday. Also on Thursday, because I think we're probably going to end up in most classes having some time at the end like this, if you want to bring like Alex questions, and I'll just go over them. Like we'll just do them in class.